Welcome back to the classroom. My name is Mr. Wong. Today we're going to be covering Module 4, Electricity and Magnetism. I'm going to focus on Inquiry Question 1 about electrostatics. And we're going to be focusing on 2 dot points. The first one is working out, using electric field line representations, we're going to try and model the direction and strength of different electric fields of these 4 scenarios. And the second part of this lesson, we are going to look at quantitative analysis of the forces and the electric field strength of these charged particles when they are subjected to electric fields. So that's what we're going to look into. For your lesson today, these are your textbook references. And as I said before, our intention is to depict the direction and strength of the electric fields. And we want to analyze the strength and the forces acting on these electric fields and what the charged particles experience as it passes through. Now, just to give you an idea of how we're dealing with charges. So the charge that we kind of measure everything to is in comparison to the charge of a proton and an electron. The reason being is because we know that the charge of an electron and a proton is fixed. So because we know the charge of an electron and a proton are fixed, everything else we do using this value can be measured back in some shape or form. The actual measurements we use for charge is actually given by this unit called capital C, which is coulombs. Typically speaking, 1 coulomb is actually a really large amount of charge already. So something like a lightning strike is 1 to 10 coulombs. That's really large. Typically speaking, what we're dealing with is 10 to the minus 6, 10 to the power of minus 9 is generally what we see in the real world. Okay, so just to start off with the concept of how electrostatic forces work, I'm going to show you this simulation here and demonstrate how charged particles can form attractions and repulsions. Okay, so if you have a look here, we have a balloon, we have woolen cloth, and then we have wool. So all of these are what we can say neutral. So if I move this here, move that there, it doesn't sort of stick on either way. So what we're trying to demonstrate is how do we get electrostatic attraction? Now we know the basic elements of attraction here. Okay, so we know that positive and negative charges will like to attract to each other. That's known as electrostatic forces. If we actually have a look here, there shouldn't be any attraction occurring just yet because both or all 3 objects are neutral at the moment. What we can do though, how we can induce electrostatics is if you grab a balloon, you rub it on your hair, or you grab a balloon and you rub it on woolen cloth. And we find that after that rubbing process, the balloon becomes attracted to our hair or to woolen cloths. So what's actually happening here, as you can see, when I'm rubbing this balloon onto this woolen cloth, the friction between the balloon surface and the woolen cloth surface causes the surface electrons of the wool to be transferred to our balloon here. So what actually happens now is you can see my balloon has a net negative quantity of electrons, and my woolen cloth has a net positive charge of these protons or positive charges. And what essentially happens is if I let go of this balloon, the electrostatic force of attraction between the positive charges and the electrons are going to pull them together, as you can see there. Okay, so that's what we have there. The exact same method happens when you rub your feet on a carpet surface and then you zap a friend. Now what's actually happening here is there's a little tiny air gap between your finger and your friend or your mate's skin. And what's actually happening, that zap is actually the transferring of electrons in the air from your fingertip to your friend's skin. Now let's have a look at the wall. Okay, so our wall here is neutrally charged. The question is, will this balloon be attracted to the wall? If we put it closer, like that, you can see the balloon is attracted to the wall. Now the question is obviously why. You probably can see here the electrons of the balloon is causing a strong repulsion against the surface electrons on this wall here, pushing it away. So by pushing those electrons away from the surface of the wall, you expose just the positive charges on the surface, and that causes a strong attraction between the balloon surface and the wall. So that's how you can cause charged particles, so charged objects being attracted to charged objects, or charged objects to neutrally charged objects. Okay, now we're back and let's go on from here. So we do know that positive and negative charges are attracted to each other, and the reason being is because of an unbalanced quantity of electrons and protons. This works in ionic bonding in chemistry. In ionic bonding in chemistry, the reason why a cation, a positive charge, is bonded with an anion, negative charge, is because there is a deficiency in the electrons in the case of the cation. So we have 10 negative charges and only 11 positive charges, while as the anion has 18 negative charges and only 17 positive charges. So that causes for net unbalanced charge on the two particles and that, or the atom, and that causes the force of attraction, which we call electrostatic force. So that's the origins of that. If we want to look at how things attract, obviously, as we said, like charges will repel against each other, and so like charges will go in the opposite direction, and opposite charges will attract. So that's what we're dealing with here in terms of electrostatic forces. You might even want to write that down. Okay, so the next question is, how can we present these electric fields? How can we model to show the direction in which it's traveling, the strength of the electric fields produced, in this case, a simple point charge, pairs of charges, dipoles, and parallel charged plates? So obviously, firstly, we need to talk about what these mean, and then we talk about the overall structure. Okay. When we talk about electric field, magnetic field, gravitational field, the concept of field in physics is a region of space where there is a particular value for every particular region we're observing. So we have, temperature fields, air pressure fields, altitude fields. In geography, they use tomographic maps. So as you can see with tomographic maps, there are specific lines that tell you specific values of where the height of the actual mountain or hilltop, and we also can tell from these lines, the denser or the closer packed these lines are, the steeper the rise is, and we know that the further spread apart these lines are, the less steep of a rise we're seeing as well. Okay, so the concept of fields, if we apply it to charged particles, can experience a force. So a field in which objects experience a force are known as force fields. In the example of charged particles in an electric field, it's going to experience electrostatic force. Remember, electrostatic force can be in terms of attraction or repulsion. So that's what we have. We do know for a fact though, any charged particle can generate its own electric field, but it won't be affected by its own field. So capital Q charge here, it won't be affected by its own electric field, but it will experience a force of repulsion from this charge here. Okay, so let's now look at trying to depict the direction and working out the field strength of the different types of electric fields. The first one we're going to look at are called electric fields for point charges. Now the thing that you need to understand for point charges is the electric field is going to move in all directions. So we call it sort of a radio field. So if we have a positive charge or a negative charge, the electric field will go in all directions. If I drew a line around it, it'd be a nice little circle. What we do know is for positive charge, it's always going outwards. And for negative charges, it's always going inwards. Where you can see the electric field lines clumping up the closest, that's where you have the strongest field strength. So the closer the field lines are to each other, the stronger it is the actual electric field strength. So let's try and show this on the simulator. So I know that the positive charge, as you can see here, if I depict the electric field strength and the direction, you can see that the field is going out. What you can also see is, if we're looking at the field strength, it's actually getting weaker as we go further and further away from the field. I can actually test that out. So if I'm at the center of this electric field, I can see the potential of the field is getting smaller as I progressively get further and further away from this field point here that we have. Okay. Now the next one we're going to look at is called the charged pairs. And for the charged pairs, what we'd refer to that is charged particles have the electric fields that are formed by particles of the same charge type. So if I have two positive charges, if I have two negative charges placed next to each other, this is the type of electric field I'm talking about when we talk about charged pairs. Just notice when we draw electric field lines, the lines will never cross over with each other, so there's no overlapping. The field can only go in one direction. The density of the lines will represent how strong the electric field is. Okay, and what we also know is if we're dealing with the same charge, we should draw the same number of magnetic field or electric field, sorry. If we were to, in a case where the electric field or the charge of the electric field is different, so let's say that with this positive charge, it was 2 plus, and this positive charge was 1 plus, then we would have to draw double the amount of lines in comparison to the +1 charge. The other thing I want you to take a note of is when we have the same charge types, there has to be an isotope line. So an imaginary line that you want to draw when you're drawing these kind of diagrams where the field lines never meet. And the reason for that is because we want to show for the repulsion. So the isotope line demonstrates the repulsion force between the two similarly charged or similar charges. Okay, so let's show that in the simulator. Okay, so I have my positive charge here. I'm going to add another positive charge, and you can see that strictly speaking, there will be a really strong sort of isotope line that will separate between the two fields. Okay, so what you can see here, if I just sort of mush it like that, you can see that it's radiating outwards in all directions. However, it reaches a point in this center point here where the fields essentially are repelling against each other. So they're not they're not moving towards each other, there is no attraction. Okay, the actual idea is if there is an attraction between the two charges, then the field line should connect up. The fact that we don't see this here means it's a repulsion of some sorts. So if I actually change this positive charge and use a negative charge, this is where we start talking about a dipole. So a dipole is when we have a positive and a negative component of the electric field. You can see what's happening here is the electric field is migrating from the positive charge and it goes all the way to the negative charge here. You can see the electric field lines are connecting from one end, the positive end, to the negative end. And so this combination represents attraction. If I was to put this one here, this is representing repulsion here. Okay, and what you will also see is the center point here has the highest electric field strength, and then it gets progressively lower as we go away from there. So that's being consistent to what we're talking. Okay, so that's being consistent to what we're talking about. All right, so as I said, dipoles are electric fields that have formed from a positive and negative end. You can imagine having two oppositely charged particles, each with their own unique electric field. When combined together will produce a singular field, which, you know, the electric field moves from the positive charge to the negative charge. You can actually see something similar to this in everyday molecules. So say for water, water is made out of H2O. We know that oxygen, when combined with hydrogen, will like to take up more of the electrons, and so it causes a more negatively charged space, what we call a partial charge, whilst the hydrogen ions will take up more of a positive partial charge, and so that's how they sort of get attracted to other molecules of water. Because if I had another water molecule, the partially negative charge of the oxygen will attract with the hydrogen, and the partial positive charge of the hydrogen will be attracted to the partial negative charge of the oxygen there. Okay, so if we want to sort of differentiate the difference between the two, remember, if it's an isolated positive charge, electric fields are moving away from our charge. And if we have a negative charge, here you see it's 2+. So not only is the field going into the page, like so, but because I drew 6 lines in the +1 charge, that means the 2-, not only is it going into the particle here, it's also got twice the amount of electric fields. So that's how you draw it, like so. Okay, and like we said before, when we talk about partial charges, this is also a representation of dipoles that we have. Okay. The other one we have is charged plates. Now you can see here how the lines are equally distant. So from about here to here, we can see that there is equal spacing. So there is equal spacing of electric field. I'm going to call it the E field. It's actually the notation we use for forming this, so that's why we use that. You can see there's equal spacing, which means that the strength of the electric field here, strength of the electric field is uniform. Another word of saying it's uniform, it's the same. Okay, it's equally separated, equally distanced, so it has the same electric field strength. You can see on this side here and this side here, they're not equally spaced, so there are variations in electric field strength if we're talking about the sort of outer edges of this charged plate. Okay, so there you go with that. Right, So again, like we said, some key features. Also remember that the electric field is perpendicular to the charged plates. Okay, so you can see it's nicely perpendicular, like so. It doesn't radiate out in all directions, rather it's just perpendicular to plate going either down or up. Evenly spaced and parallel to each other. The reason being is because we're showing that it's going in the same direction and it has the same strength. Okay. The next bit is obviously comparing the different types of strength of the electric field. So imagine you have a charged particle, X and Y, same type of charge. So let's say it's +1, some arbitrary number, and we place it in all these different electric fields. Think about which one will experience a stronger electric field strength, okay, or which one will be in a stronger electric field region. Okay, if you want, you can pause the video here before I go through the answers. We'll go through it in 3, 2, 1. Okay, so if we look at this diagram here, if we try and draw out the circle point, remember, if we can draw out the circular component of where the electric field is, we call this the equal potential point. What that essentially means is the E field strength is the same. Okay, if you can see, Y is on the edge of the circle, while as X is inside the circle. So X is going to be experiencing a stronger field strength. So this one is a stronger experience. X and Y, you can see the distance between the arrows are the same, so they are the same. If we look at question C, we can clearly see that Y is closer to the center and the lines are more densely packed. So this Y is the stronger one, or at least experiences the stronger field. D, this one would also be Y, it's closer to the charges. So this one will be stronger. If we have a look at this one here, so obviously depends on where you draw the circle, but you can see they're sort of within the same circular boundaries, within the same equipotential point. So they both experience about the same electric field strength. And then if we have a look at what we have here, we can see that our charges sort of experience a very similar field strength as well here. So if we just have a quick look, compare the distances of the two, it's about the same. So they're sort of the same that we're gauging here as well. Okay, that basically concludes this part of the lesson where we talked about how electrostatic forces are created. We also talked about how we depict electric fields for point charges, for charged plates, dipoles. The main takeaway you really need to remember is the electric field of a positive charge is always going out in a circular formation. We also know that if we double the charge, we increase the quantity of electric field lines. So roughly around so. We know that if it's positively charged, so if we have two positively charged pairs or two of the same charges, they're going to repel, and we can represent that sort of as an isotope line. If it's the opposite charges, it's going to go from positive to negative. And we also worked out if we have two charged plates, let's say this one's positive, this one's negative, we said that the electric field is going to be perpendicular to the plate, and we'll have even spacing. Hopefully this is nice and even inside the two plates. Outside is going to be some slight variations. So that explains how we represent electric field strength. Our next part of this lesson, we are going to talk about and calculate the electric field, an actual numerical value of the electric field strength of these different electric fields. And we're going to look at the amount of force that charged particles will experience when they move inside the electric fields of the ones that we talk about here. All right, onwards to the next lesson.